Hello everyone, this is the fourth part of the chapter Reactions at Alpha Carbon of Carbon Compounds. And in this video, we are going to talk about enolate ion and how do we form the enolate ion and what are some of the applications of the enolate ion. Okay, so to begin with, the amount of carbon compound that can be converted to an enolate ion depends on two different factors. The first factor is the pKa of the carbonyl compound. And the second one is the base that is actually used for removing the alpha hydrogen. Okay, now let's take let's try to form the enolate from hexanone by reacting it with two different bases. In the first case, I'm taking OH minus. So for when OH minus is used, the amount of enolate that is formed from this reaction is actually less than 0.1%. Okay, and along with this you will also have some amount of water that is liberated. Okay, when you identify the pK of the two, when you compare the pK of the two different acids in the equation, cyclohexanone has a pK of 17 and water has a pK of 15.7. So we know that when there is an equilibrium between the two reactions, the equilibrium will always shift in the direction where the weak acid is present. So the weak acid right here is cyclohexanone, and therefore the reaction doesn't go to completion, or there is low amount of the product that is formed. Okay, suppose if you're going to react the same cyclohexanone with LDA, which is lithium diisopropylamide, lithium diisopropylamide, the reaction is going to be almost complete with the product yielding to about 100%. Okay, so this is actually going to be in resonance with the other tautomer, even here. Other tautomer. I'm not going to draw the structure for it. I hope that you guys know how to draw the structure. Okay, and along with that, you will also get the diisopropylamine. So this is diisopropylamine, which is the conjugate acid of diisopropylamine. When we compare the pK of the two different acids, again, pK of cyclohexanone is 17 and the pK of diisopropylamine is 35. And here, this is the weak acid. And the reaction is actually going to shift to the right. Okay? And therefore, you get a very high yield of 100% here. Okay, now, how do we prepare LDA? LDA is prepared by adding butyl lithium to diisopropylamine in THF at minus 78 degrees Celsius. Okay, so we'll do the reaction here. So this is diisopropylamine. Okay, when it is reacted with butyl lithium. Okay, remember butyl lithium is an organometallic compound which has a negative charge on the carbon. So the carbon is going to act as a nucleophile. Okay, and it's going to go grab the hydrogen from here, thereby forming the base. So this reaction normally takes place in THF at minus 78 degrees Celsius, and you form the corresponding nucleophile. Okay, so and you will also get the alkane. Okay, and this structure right here is LDA. Remember, LDA is a very strong base, but it's a poor nucleophile. Why it is a poor nucleophile? Because when you look into the structure of it, you can see all those bulky groups that are the two isopropyl groups on either side of nitrogen. Is going to make it a very bad nucleophile or poor nucleophile. Hence, it removes an alpha hydrogen faster than it adds to a carbonyl carbon. Okay. So now we are going to talk about the applications of LDA. LDA is primarily used for alkylating the alpha carbon of carbonyl compounds, which is another way to form the carbon-carbon single bonds. Okay, so let's do an example here. This is cyclopentanone reacting with LDA. Again, we use THF as the solvent, and you form the enolate, which is the first step. So where the LDA is going to go grab the hydrogens and it's going to form the enolate. Okay, and in the next step, these electrons are going to shift in here. Double bond is going to break, and which is a resonance structure for the other tautomer, which is the structure for the other tautomer. And now, if you want to react it with, an alkyl halide, okay, what happens here is these electrons are going to come up here, and this is going to act as a nucleophile attacking the electropositive carbon of the alkyl halide, and is going to thrust the electrons onto bromine, making it a Br is going to be the leaving group, and it's going to leave. Okay, and the product that you'll be getting for this reaction is it's the monoalkylated cyclopentanone. Okay, so lithium diisopropylamide is used for alkylating the alpha carbon of the carbonyl compound. So as you can see, the hydrogen in here is replaced by a alkyl group. Okay, now what type of reaction is this? This is exactly the same reaction that we just talked a second ago. And what type of reaction is this? Again, this is remember, the main reaction that the alkyl halides would undergo is the substitution reaction. So if this is your alkyl halide right here, in the place of bromine, you have this group right here. So this is a substitution reaction, nucleophilic substitution reaction. Okay, what would be the difference in products when there is a strong base and a weak base? When you compare the basicity of LDA with the OH, LDA is more strong, and it is used primarily to make more of the product. Okay, so when you react cyclohexanone with LDA, you basically get only one product, and the product right here would be this, which is monomethylated cyclopentanone. Okay, but when you're going to use OH, which is a weaker base, comparatively weaker base, with LDA, and reacted with the corresponding alkyl halide, whichever alkyl halide that you wanted to use based on the alkyl group that you wanted to put it in the alpha position. Okay, here you will get a mixture of different products. Okay, so after monoalkylation, there is still a lot of base that is present, and therefore it is going to form the di, tri, or even tetraalkylated product. So you can see that after the monoalkylated product is formed, there is also going to be some amount of base present, so which is going to grab the hydrogens in here, grab the hydrogens in here. So accordingly, it's going to form the di-substituted product, and then again, this hydrogen will be, so this hydrogen, both of these hydrogens can also be abstracted by the base, and it's going to form the tri and as well as tetra substituted product. So if you wanted to get only one product, LDA is the best base that you can use. Okay, what other carbonyl compounds can be alkylated on the alpha carbon using enolate? So normally you can use aldehydes and ketones, okay, but you can also use esters and nitriles. And again, the mechanism is going to be the same. Okay, so what you do right here, here you have the two alpha hydrogens. There are two alpha hydrogens, and one of those hydrogens will be picked up by LDA, and then the enolate ion will be formed, and the enolate ion will react with the alkyl halide right here. So remember, this is going to act as an electrophile. The carbon is going to be electropositive, and the enolate ion, which is a nucleophile, is going to go attack this carbon, and the leaving group I is going to leave, thereby forming this product. Okay, so remember, this is also alpha alkylation. And the same thing can also happen with nitrile. So if this is your functional group, the next position is alpha. So the hydrogens in here is replaced by an alkyl group. Okay, again, you can tailor the alkyl groups based on your need. Okay, let's see what's going to happen when you want to alkylate an unsymmetrical ketone. Here is an example for an unsymmetrical ketone. Okay, in an unsymmetrical ketone, the LDA has two different kind of chances for abstracting the alpha hydrogen. So for this particular compound, there are two different types of alpha hydrogens. So on this is the alpha carbon, and it has two alpha hydrogens, and this is another alpha carbon, which has one hydrogen. So now, which of these hydrogens is readily accessible for LDA? Okay, obviously it is going to be these hydrogens, because here the methyl group is going to be a steric hindrance for the hydrogen abstraction. Okay, again, for any product to be a kinetic product, it has to occur super fast. Okay, so when the LDA comes and abstracts this hydrogen, these electrons are going to hop in here, and that's going to thrust the electrons onto oxygen, forming the enolate ion. So here is the enolate ion. Once after this enolate ion is formed, which is going to be like really fast, it's going to react with alkyl halide. Okay, and this product is formed, which is a kinetic product. Now, the thermodynamic product is usually going to be the most stable product, but the enolate ion, for the enolate ion to be formed, it's going to take a little bit of time. Okay, the LDA is still going to go access this hydrogen, but it's going to take a little bit of time for it to form the enolate ion. Although it takes some time, it's going to be the stable enolate ion, because you see the double bond right there. According to the Zaitsev rule, this is the kind that has the most stability. Okay, because it's actually tetra substituted, and probably you must have studied in alkenes. A tetra substituted alkene is going to be more stable than a tri substituted alkene or a di substituted alkene. Okay, and then once it forms the stable enolate, it's going to do the nucleophilic attack on the alkyl halide, thereby forming the thermodynamic product. Okay, so with unsymmetrical ketones, you form two different types of products.